So next, I want us to look at regression analysis, and we start by saying that regression analysis is a measure of the average relationship between two or more variables. Okay. In the context of correlation analysis, our objective was to check the strength of relationship and also the direction of relationship between exactly two variables. But when we come to regression analysis, we attempt to find what we call the cause and effect relationship. So we measure the cause and effect relationship between two or more variables. So in this context, you have a variable which is being predicted and another variable which is predictor. Okay. Usually the predicted variable is denoted by Y, but it can be denoted by any other letter, and the predictor is denoted by X. Another name for the predicted variable is the dependent variable. You can call it the dependent variable. And another name for independent for the predictor variable is what we call independent variable. There are other names that can be used, but in this case, in this class, I'll only be using dependent variable or independent variable. Usually the predicted variable is explained by the predictor variable. Okay, and in this case, we believe that there is a cause and effect relationship between the two variables. That's where the concept of dependence comes in, where we believe that one variable is affecting the other variable, but not the vice versa. So the objective of regression analysis is the prediction. The objective of regression analysis is a prediction or the estimation of the dependent variable for given values of the independent variable. So if you're given some values of the independent variable, that is X, we use regression analysis to estimate the values of, or to predict the values of Y, or the values of the dependent variable. Now, what are the types of regression analysis? And there are different types of regression analysis. For example, we have simple regression and multiple regression. Okay. Then we have what we call linear and non-linear regression. Linear and non-linear regression. Then we also have what we call total and partial regression. Partial regression. In your course, you'll be focusing more of the first two in your course, either in this class or even in another class like econometrics. We'll be dealing with nonlinear regression. So in this class, we'll be talking about these two. We'll be talking about simple linear regression, which is coming from here and here. Then we'll also be discussing multiple linear regression. Multiple linear regression. So we'll be discussing this and that again. So meaning that we'll not be discussing nonlinear regression, whether it is simple or multiple, that will be covered in another class. So let's start with simple linear regression. Simple linear regression. So maybe before I explain what that one is, I may want to start by saying that simple regression is a regression that contains or that entails only two variables, say X and Y. Multiple regression is variable that entails more than two variables, say X, Y, and Z, or maybe W, X, Y, Z, or X1, X2, X3, all the way to Xk. That's multiple regression. When we talk about linear regression, this is a type of regression where we assume that the variables have a linear relationship. In other words, the relationship between or among the variables can be represented by a straight line. The non-linear regression, this is where we assume that the relationship between or among the variables is non-linear. It's either quadratic, it's either cubic, it's exponential, it's logarithmic, and so on and so forth. In this class, I'll not want to mention or to go into the details of what is total and partial regression, but you can check it out. You can check it out later. So what is this now? Simple linear regression. By combining what we have just said there, then it means that simple linear regression is a regression which involves two variables, and we assume that the two variables have a straight line kind of relationship, or they have a linear relationship. So we can say, in simple terms, is a model involving two variables which have a linear relationship. One of the variables is called the dependent variable. We have the dependent variable, and the other variable is called the independent variable. Independent variable. Okay. So let's consider two variables x and y. Consider two variables x and y. Okay. Then we say the linear regression, let's say the simple linear regression of y on x is given by the equation y is equal to beta naught plus beta 1 of x. So that is a simple linear regression equation of y on x. I know you remember equations of this format. Those are the equations we are talking about. Or maybe y is equal to, if you remember equations of this format, those are what you call equations of a straight line or linear equations. So when you talk about simple linear equation, simple linear regression, we're talking about the same. It's only that now in the context of regression, the convention is to use the Greek letters betas as the coefficients instead of using A and B. But if you decide to use A and B, there will still be no problem. But the convention is to use betas, either beta naught, beta 1, etc. Okay. So, so in this case, so here, y is the dependent variable and x is the independent variable. Then this guy here and beta 1, these ones are known as the regression coefficients. They are known as the regression coefficients. Sometimes you can call them regression parameters. I believe the term parameter is not new to you. A parameter is a numerical summary value for the entire population. Okay, and just like any other parameter, these regression coefficients are always unknown. They are always unknown. So the values of beta naught and beta 1 are always unknown. So if they are unknown, you need to know that we need to estimate them. If they are not known, we need to estimate them. So we need some method to estimate them. But before we look at that, I also want you to contrast this scenario. I want you to contrast this scenario here so that you don't confuse some things. So let's say the regression equation, of x on y. I want you to see the difference. Huh? This is y on x. That is the equation. So the regression equation of x on y is given by, let's say x is equal to, let's say beta naught, you can put a star there, plus beta 1, put a star there, and you say y. Okay, Beta naught star, beta 1 star are just betas, so they're just some unknown constants. But in this case, this guy here is your dependent variable. And in this case, this is your independent variable. So what becomes your dependent or independent variable relies on what are you regressing on what? What are you regressing on what? You regress the dependent variable on the independent variable. So it's good that you get it right so that you don't have the wrong kind of regression. Because if you have this kind of regression here, if you have this kind of regression, instead of this, then you can be sure that you are going to estimate the wrong parameters because these values will be different. Because you'll be getting beta naught star instead of beta naught, or you'll be getting beta 1 star instead of beta 1. So it's good to note this bit. Know what you are regressing on what. Okay. Now, let's consider the first. So we'll continue the first scenario where we are regressing y on x. Okay. So let's say that beta naught is known as the y-intercept. And then beta 1 is known as the slope or the gradient. That's the gradient of the line. The gradient of the line. Because remember, we are dealing with some straight line. So this straight line here has a point where it is cutting the vertical axis, and it also has some slope if it is not a horizontal line. Okay. So now, as we've mentioned, is that beta naught and beta 1 are always unknown. So we need to estimate them. So for you to estimate the values of beta naught and beta 1, you need some data, which will be coming from a sample. So there are various methods of estimating the values of beta naught and beta 1. But the method that we're going to discuss in this class is known as the ordinary least squares method. Or OLS method. And I want to briefly explain what the OLS method is all about. So you start by having some scatter plot somewhere. So we are regressing y on x. So if you are regressing y on x, it means that y will be on the vertical axis and x will be on the horizontal axis. Suppose you do a scatter plot, and then these are the points that you have on your scatter plot. To make it simple, I'll assume that I have only 5 points. So regression analysis is all about coming up with a straight line which passes through the points in such a way that, or in an optimal way, let me put it like that. We need a line which passes through the points in an optimal way. If it was in a perfect scenario, we'll be having a straight line which passes through all the points. So if you have perfect positive correlation, for example, your points are like that. If those are your points, then a regression equation, a regression line is a line that passes through all the points like that. But you notice that in most of the scenarios, the points are not all lying on a straight line. So they're like the ones illustrated here. In such a case, you need a line which passes as close to all the points as possible. So let's say the line passes here. Assume that is a line. But you know, it may not be the line, but we need a line which passes through the points in such a way that if you measure these vertical distances, let me start with these. Let me call this one E1. I also measure this, you call it E2. You also measure this, you call it E3. This one, you call it E4. And you call this one E5. Okay, so let me have the point like this. All the points are visible. So we need a line in such a way that if you draw the line or if you fix the line, then you measure those vertical distances, then you square them such that you have E1 square, and then you also have E2 square. You square all of them, then you sum. So let me put the summation here, plus E3 square plus E4 square plus E4 square plus E5 square. So you take the vertical distances, you square each one of them, then you sum that. Such that if you do this, you get, let's say this is S. Let's just call it S. So in other words, we are saying that S is summation of EI, and maybe for I is equal to 1 all the way to N. N is the number of observations. In our case, it is 5. So it is E1 plus E2 like that. So we need a line which minimizes this function here, such that when you sum this, you get the smallest possible number. In other words, you minimize this function here. We need a line which passes through the points in such a way that S is minimum. That line, if it exists, we call it the line of best fit. That's what we call the regression line. So we need to fix the line somewhere. So it means that we don't have so many such lines. There's only one line which does this, which minimizes the sum of square of those errors. I'm calling them errors. That's why I'm using is sum of square of those errors. Okay. And you will notice that what I'm calling E here is Y minus Y hat, where Y, this is the observed value. This is the observed value. That is the point, that is a dot, like this dot here, it's a Y. But this guy here is the predicted value. And the predicted value is represented by this line here. So this point here corresponds to Y hat, another Y hat, another Y hat, another Y hat, another Y hat. So the difference between Y and Y hat is what I'm calling E. So in other words, I need a line which will minimize this, the difference between the values observed and the values predicted. That's what we call the line of best fit. And from calculus or from differentiation, you know that there are various ways of optimizing, like of minimizing or maximizing functions. So if you want to minimize a function, what do? You differentiate once. Then you equate that derivative to 0. And I want you to note that this predicted value here, this Y hat here, is some function of, sorry, let me say this. So this function, this S function here, this function S here is a function of beta naught and beta 1. So it is some function which contains beta naught and beta 1 as the variables in this case. So even when we are trying to minimize, we are minimizing this function with respect to beta naught and also with respect to beta 1. The way you would get an equation like this, Y is equal to a function of X and W. Like for example, Y is equal to X squared plus 2W. And you want to minimize or you want to optimize this function. So you need to differentiate this function with respect to X equal to 0. You differentiate this function again with respect to W equal to 0. So in our case here, S is a function of beta naught and beta 1, the regression coefficients, the unknowns. So you differentiate some function with respect to beta naught, and you differentiate again the same function with respect to beta 1. Then you equate those two scenarios to 0. Once you do that, you will end up with some two equations. So the process of minimizing this function S leads into two equations, which we call the normal equations. And the normal equations are just some linear equations. Okay. there are some linear equations which we can solve very quickly using very simple mathematical techniques to find the values of beta naught and beta 1. So if we are regressing, so if we are regressing y on x, and we say that the regression equation, I'm repeating myself, is of the form y is equal to beta naught plus beta 1 of x. And the corresponding normal equations are and in this case, we are going to have two normal equations because our function s has two unknowns. So we're going to differentiate with respect to x. With beta naught, we get one equation. We differentiate again with respect to beta 1, we get another equation. If you are dealing with a multiple case, like we'll see later, when you have three regression parameters, that is beta naught, beta 1, and beta 2, we shall end up with three normal equations. So the first normal equation looks like this. And usually you just modify this expression here, beta naught plus beta 1 of x. You sum up this item n times. I believe you have some data somewhere, x and y. So this is the y we're talking about. So I want us to sum y. So here you have y1, y2, all the way to yn. So when you sum up these values, you get y1 plus y2 plus all the way to yn. So that gives you summation of y. So the first value here is summation of y is equal to, then you also do the same to this guy here. These are constant, it's a number. You have beta naught, you have beta naught, you have beta all the way and beta naught here. Remember, we have n observations, so you have beta naught plus beta naught plus beta naught all the way to plus beta naught n times. So when you add that, when you add all those beta naughts, you will get n beta naught. You will not get summation of beta naught. It's like when you have 2 plus 2 plus 2 plus 2 plus 2. When you sum this, you don't get summation of 2 because it doesn't make sense. But if this is what you have, you can say this is 1, 2, 3, 4, 5 times 2. The same as 5 times 2 is 10. Okay, and it's true. If you add these values, you get is 10. So when you sum beta naught n times, you'll get n beta naught. Then finally, you come and sum this term here, which will give us beta 1 summation of x. It's like you have 2x, then you want to sum. It's like you get some 2 summation of x. So that's the first normal equation. Now the second normal equation looks like this. This is how you make the second normal equation. So again, you start from the original equation or the required regression equation, which we said is y is beta naught plus beta 1 of x. So we have used this equation the way it is to get our first normal equation. So to get the second normal equation, you take x and multiply everywhere in this equation by x. So you'll end up with xy is equal to beta naught x plus beta 1 x squared. Then you sum. You take x, which is the independent variable, multiply everywhere by x. Then you sum the resulting equation, every term of the resulting equation. So this becomes summation of xy. That is, you sum this, then you sum this. This gives you beta naught summation of x. Plus, you sum this guy here. You'll get beta 1 summation of x squared. And these two are the normal equations that you need to solve. These are equations of a straight line, what you usually call simultaneous equations. In other words, equations that can be solved simultaneously. So these are equations, and everything in this equation is known except those two guys. Those are the only guys who are not known, and they are the ones that we want to find. They are the ones that we want to solve and get. Summation of y, you'll get it from your data. Because we'll have some data somewhere, you just need to sum the values of y. N is the number of observations in the data, so that should be easy to get. Summation of x, you'll get it from the data. Summation of x and y. Summation of x multiplied by y, you'll get it from the data. Actually, if you recall what we were doing in correlation analysis, you know how you can get these values of summation of y, summation of x, summation of xy, summation of x square. You can quickly get them from your calculators if you don't want to do it manually. Okay, so we need to say that you solve these equations simultaneously to obtain estimates of beta naught and beta 1. And these estimates of beta naught and beta 1 will be denoted like this: beta naught hat and beta 1 hat, respectively. So the answers that you are going to get from after solving these equations, you'll be denoting them as beta naught hat and beta 1 hat to show that they are the sample estimates of the unknown population parameters beta naught and beta 1. Hope that is clear. So to make it more clear, let's have an example. So I'm going to write down some data. Then we obtain or we fit a regression model to the same. So let's consider the data below, and then we are required to fit a simple linear regression equation with a simple linear regression of y on x. In other words, regress y on x. Regress y on x, or to predict y for given values of x. So when you're given a question like that, you note that we need an equation of the form y is equal to beta naught plus beta 1x. We need an equation of that format. So once you know the equation that you need, then you need to write down the normal equations that correspond to that regression equation. So the normal equations corresponding to that are summation of y is equal to n beta naught plus beta 1 summation of x. Then we have summation of xy is equal to beta naught summation of x plus beta 1 summation of x square. So those are the normal equations that we need to solve. So for you to come up with the required equations, you need these values. You need summation of y, which you can get directly from the data. You need the number of observations, 1, 2, 3, 4, 5, 6, 7, n is 7. You need summation of x, which you can get from the data. Okay, so we have seen how you get each one of those. You need summation of x times y, so you need to add another column here, x times y. Then you sum it down here, summation of x, y. You need, we have that already. You need summation of x square. So you need x square there. So that down here you can do summation of x square. And we saw that you can obtain these values from your calculator. You can obtain these values from your calculator. So someone help me get summation of y. We know n is 7. Summation of x. Summation of xy. Summation of x square. So once we get those values, we plug them into our normal equations, then we'll end up with some simple equations which you can solve quite fast. So after obtaining the values of the different summations, these are the values we have. You can quickly get them from your calculators, or you can just do them manually by completing this table. Then after that, you plug them in and you form such equations. This is what you're calling the normal equations. As you can see in the normal equations, we only have beta naught and beta 1 as the unknowns. And those are the values that you want to find out. Those are the values that you want to get. So this being a system of linear equations, you can solve using either the elimination method, you can use substitution method, you can use matrix method. And in a case like this, you can even use a graphical method to solve for the values of beta naught and beta 1. So I don't know which method is okay with you. So let's use a substitution method to solve the equation or to solve the system of linear equations. So we're going to use this method. And we label the equations as Roman 1 and Roman 2. Then using Roman 1, we make beta naught the subject of the formula. So it means that we take this guy to the other side. And then we divide both sides by 7. So we have 476 minus 469 beta 1 divided by 7. Then you call that as your equation number 3. Then you substitute that equation number 3 into the second equation, into Roman 2. So where there is beta naught, you put this guy here. So equation number 2 becomes that 1917 is equal to 469 multiplied by the new value of b, of beta naught, then plus that 451 beta 1. Then after simplifying by dividing this term, the first term, by 7, we'll end up with this item here. We'll end up with that. Then after grouping like terms together, we'll get 25 is equal to 28 beta 1. Then after you make beta 1 the subject of the formula, you will get this as the regression coefficient, beta 1. And we said this is always an estimate. So you put a hat there to show that that is the estimate of beta 1 using this particular method. Then now using this value here, you can use either equation 1 or 2 to obtain the value of beta naught. So let's do that. So in order to obtain the value of, or the estimated value of beta naught, we work from equation number 3. And from equation number 3, this is what we have, that beta naught is given by that. So, but we also know that the value of beta naught, what we've just obtained in the first part, is 25 over 28. Or you can work with the decimal value, still okay. Then plugging in that value here, you'll end up with beta naught is equal to that value. And again, as we said, is that this is an estimate of beta naught. So you put a hat there. You put a hat there. So remember or recall that when you have keyed in this data, if you have entered this data into your calculator, memory of your calculator, when you go to SVAR, and then you press the navigation key, you will see these 3 options, where we said that the last option here, this is the Carl-Pearson's correlation coefficient. This is your R, Carl-Pearson's correlation coefficient. Then this value of A here, which corresponds to this 1, 2, and 3. So this one is beta naught, and this one is your beta 1. So you can always confirm whether your answers are correct using your calculator. But in an exam setting, you need to show the steps. You need to show the steps, how you form the normal equations, how you use the summations, how you use elimination method or substitution method, or whichever the method, to obtain the values of the estimated values of the regression parameters. So once you have the regression parameters, you're good to go. Now we can say that the required regression equation is this, or is given by, you say y is equal to beta naught, which is 8.179 plus beta 1x. Beta 1 is 0.893 of x. So that is the required regression equation. So if you are told to fit a regression equation of y on x, then once you solve the regression parameters, that's what you have. But remember, this is an estimate of beta naught, and this is an estimate of beta 1. So even here, this is an estimate of y. So you also put a hat on top of y. So this is the estimated value of y. So y hat here, this is the estimated or the predicted value of y given x. If you are given the value of x, then that is the predicted value of y. If you remember where we started, that is this line here. This line here is what we are calling the y hat. And I think I mentioned that. That's the y hat. Then the observed data, that is your y. That is your y. Okay. So the next thing after you fit the regression equation is how do you interpret the regression coefficient? So interpretation. And we start by the interpretation of this value, which is 8.179. Basically, we say that this is the estimated value of y. This is the estimated when x is 0. In other words, if you put 0 here, if you put 0 there, then this is the estimated value of y. That should be straightforward. Then the interpretation of the other value is much more interesting. Beta 1 hat, which we're saying is 0.893. This is the slope coefficient, and you say that this is how you interpret the value of beta 1. We say that the estimated value of y that is what we are calling the y hat, increases by 0.893 units for every unit increase in the value of x. In other words, for every unit increase in the value of x, then this is what happens to y. It increases. In other words, is a positive relationship. When you increase x, then y increases because this value here is a positive value here. It's a positive. So this sign here matters. Tells you that it's an increase. If it was a negative, we would say that if it was minus 0.893, I would say that the estimated value of y decreases by 0.893 units for every unit increase in the value of x. So for example, if your x was 10, or let's say if your x was 0, for example, if your x is 0, if your x is 0, then what is y hat? If you plug in 0 into this equation, your y hat will be 8.179. But if you have x is 0 plus 1, which is 1, if you increase x by 1 unit, then what happens? In other words, if you put a 1 here, if you put a 1 there, then your estimated value of y will be 8.179 plus 0.893 times 1, which is what? Which clearly means that y increases by, which is the same as 8.179 plus 0.893. So once you increase x by 1 unit, then y increases by 0.9893. And that is true for other values of x. You can check for, I want you to do this later. Check for x is 10 and x is 11, because that's a 1 unit increase in the value of x. I want you to check the values of y and also y here. You will notice that once you increase x by 1 unit, then the value of y will always increase by 0.893. That's the slope of the line. It's a constant slope. Okay, so that is it. So maybe the other thing that after you do this that you may want to do, which is not within the scope of this class, is to test the significance of this. So you perform hypothesis testing to check whether these coefficients or this slope is significantly different from 0 or from any other hypothetical value. But that's a story for another class. Okay, so that is it about simple linear regression.